Welcome. Let's begin with a prayer. Lord, we thank you for this beautiful creation that you've given us, this whole universe. We thank you for coming into the cosmos to redeem us. Help us to learn more about this world you've created so that we can also learn more about you, as well as learn more about ourselves. Inspire us with your Spirit and guide us in the path of truth. We ask this through Christ our Lord. Amen. Hello, I'm Mr. Ahern, and I will be guiding you in this semester-long journey through astronomy. This course is divided in two halves. In the first half, we will be going through astronomy historically, from the ancients to today, and in the second half of the course, we will be looking at astronomy systematically, from what's closest to us on Earth to what's farthest away from us in the universe. In a liberal arts education, the quadrivium consisted of 4 subjects: arithmetic, number; geometry, number in space; music, number in time; and astronomy, number in space and time. As humans, we want to understand the physical universe we live in, and as Christians, we want to understand the cosmos that our God, the Logos, created. Before we begin the astronomy content, however, we need to explain the philosophical approach that we should take, especially with regards to the relation between faith, science, and reason. By reason, we mean not just the ability to think clearly and come up with answers to questions, but also the capacity for wisdom. The Dominican James Brent says, "Wisdom is an all-embracing understanding of reality as a whole in light of ultimate causes, especially in light of the end or goal of all things." Astronomy is an example of reason in action, but it's not the only way to wisdom. Christopher Baglow, in his book Faith, Science, and Reason, emphasizes that reason leads us to pose questions we could never use reason to answer. There's another kind of knowledge that we can get if we entrust our whole self to God, and that type of knowledge is called faith. In faith, the human intellect and will cooperate with divine grace. Believing is an act of the intellect assenting to the divine truth by command of the will, moved by God through grace. St. John Paul II began his famous 1997 letter on faith and reason in this way: "Faith and reason are like 2 wings on which the human spirit rises to the contemplation of truth. And God has placed in the human heart a desire to know the truth, in a word, to know himself, so that by knowing and loving God, men and women may also come to the fullness of truth about themselves." Because the God of our faith is also the God of the universe, and 2 truths can never contradict each other, we don't have to worry about solid science ever undermining solid faith. Whenever there's an apparent contradiction between science and faith, then either the science is not quite right, or the faith may need to be interpreted in a different way. When we talk about faith, we often use the word supernatural, which from the Latin means above nature. Note that it does not mean against nature. True faith and true science are in harmony. Johannes Kepler echoed this idea in his 1619 work, The Harmony of the World. We'll get into more detail about Kepler in week 4. But here let us mention that in this work, Kepler related musical consonants to the angular velocities of the planets in order to provide evidence for God as a grand geometer. Our knowledge of music and astronomy has come a long way since Kepler's time, and science has shown us that things are often more surprising than an initial simple view allows. But we still find amazing order in the cosmos, as well as openness, because our universe is dynamic. The first celestial object we'll talk about is the sun. We observe the apparent motion of the sun every day, rising in the east, setting in the west. And if, for those of us who are in the northern hemisphere, we observe the sun to go around to the south. And if you're in the southern hemisphere, you'll observe the sun to go around to the north. If you're in the Arctic or Antarctic Circle, then you will have 6 months of sunlight and then 6 months of darkness. The longest day of the year is the summer solstice. The shortest day of the year is the winter solstice. Now, the summer solstice and the winter solstice happen on the same day for opposite hemispheres. For example, when the northern hemisphere has summer solstice, the longest day of the year, the southern hemisphere will have winter solstice, the shortest day of the year. And now, about halfway in between the solstices is the equinox. There are 2 equinoxes, the spring equinox and the fall equinox. And on those days, it's exactly 12 hours of sunlight and 12 hours of darkness. And the sun rises due east and sets due west. The next most important celestial object is the moon. Now, we observe the motion of the moon. If you pay attention to the timing, each day it will rise about 50 minutes later than the day before, and of course set about 50 minutes later than the day before. And we see the moon's different phases. Now, the phases depend on the geometry with respect to the Earth and Sun. So there's the full moon, of course. Now, you can only see a full moon at night, but you can see the moon in other phases during the day when part of it is lit up. If you think about the geometry of the sun, earth, and moon, this should make sense to you. So we're going to talk about the motions in the sky that happen first on a daily basis and then monthly and so forth. So using Stellarium, free software, you can download this. I've gone to Baghdad, which is Mesopotamia. Of course, it wasn't Baghdad back then, but that's fine. I've gone to the year -2000 in this program, which is 2001 BC, because in this program there's a year 0, but there was no year 0. I've gone to April 1st, which is about the time of the equinox back then, so that you can see the sun will be rising just about due east. So the sun has risen now in the east, and I'm going to fast forward hour by hour, so 1 hour at a time. You can see the sun making its way across the sky to the south, because Baghdad, Mesopotamia, is in the northern hemisphere. For anyone in the northern hemisphere, the sun goes around to the south and then goes back and sets in the west. And then it's nighttime, and then the sun will rise again the next day in the east, set in the west. And as you can see, the stars are moving too. At nighttime, we can see that. And the moon is also kind of following the sun in this. Now, you may also notice some planets that are showing up here. We've got Mars and Saturn. Sirius is the brightest star after the sun. We'll be talking about that. There's Jupiter down here. And then Venus and Mercury, let's inch up by minutes. Right before the sun rises, you can see Venus and Mercury. Venus is much brighter than Mercury. Venus is the brightest planet that we can see from Earth, excluding the Earth itself. Jupiter comes after Venus. Mercury is pretty dim. It is hard to see. I've tried several times to see Mercury with the naked eye. I was able to see it once with a telescope in the evening. But Venus and Mercury, because they're always close to the sun, they can only be seen either just before sunrise or just after sunset. Now, I'm not sure if you noticed the paths that the sun and moon and planets were taking in the sky. I'm going to go ahead and turn on the ecliptic. Ecliptic is the path of the sun in the sky, and you can see that not only the sun, but also the planets travel near the ecliptic. So the ecliptic is specifically the line the sun travels on, but the planets and moon are all close to it. You see the moon close to the ecliptic there, and then Jupiter close to it, Mercury and Venus as well. Mars and Saturn close to the ecliptic. What this is basically the plane of the solar system, how all the planets orbit the sun in the same plane. Pluto, the dwarf planet, is inclined. It's not always close to the ecliptic. Lots of other objects out by Pluto, similar to Pluto, have inclined orbits, and comets and so forth that are away from the sun most of the time. A lot of those have inclined orbits, so they would not always be close to the ecliptic. But the inner planets and the outer planets are all in the same plane, more or less. They have very low inclinations. So we always see them close to this line, the ecliptic. All right, now let's talk about the moon a little bit. So when did the moon rise this day? We're already on April 7th. Okay, so so the sun is about to set. Okay, the moon rising, we can see the moon label there, and it's 5:28. So if we go to the next day, we have to go ahead from 5:28 about 50 minutes usually. So 6:18, and then we get the moon in about the same spot in the sky the next day. So that was April 8th. Let's go one more day ahead to the 9th, because it rises about 50 minutes later each day. So yeah, so there's ahead an hour, but then we got to go back 10 minutes. And so yeah, so now we've got the moon rising. So let's jump ahead a few hours. We can see the moon crossing. We can make an imaginary line from north to south. That is called the meridian. Let's see if I can turn that on. Yes. So that's the meridian. When the sun crosses the meridian, for example, that is local noon. It's not always at 12 o'clock. We use the 24-hour day, but that's the average. If we were to determine each day locally, according to the seasons and all that, then some days would be greater than 24 hours, some days would be less, and we would have the local noon be when the sun is at the meridian. But that makes things harder to plan and get used to, so we just use averages. But the meridian is when the sun or any object crosses the meridian is when it is highest in the sky. It's kind of hard to see with this view. I chose this view to be able to see this equal area view, just to be able to see the whole sky at once. We'll explore other views later on. But okay, another thing to point out, we're basically lying on the ground looking straight up. That's what we're looking at. North, south, what's going on? West is on the right, east is on the left. It's because we're looking up instead of looking down. We're used to looking down at the earth on maps, but now we're looking up into the sky. So that's a little different. Yeah, so just to reinforce the idea of the moon rising 50 minutes later, let's jump ahead one day at a time, and you notice the moon lagging back in the sky a little bit. Each day, the moon is falling back, going towards the sun, but then it'll pass it. So it takes the moon about a month to go around the earth. We get the word month from moon. It's a little bit less than what our current months are, about 29 and a half days, but that's pretty close. Okay, now let's look at the night sky a little bit. Let's go to, all right, so the sun has just set, stars are coming out. I've got the meridian on there, and some of the bright stars are labeled here. So Sirius down here, the brightest star after the sun. We can see here Procyon, Spica, Arcturus. Arcturus is the next one after Sirius in brightness. So it goes the sun, of course, then Sirius, then Arcturus. There are some in the southern hemisphere that may be brighter than Arcturus. We go forward a little bit more. We see other stars, Vega and Altair. These are two of the stars of the summer triangle. The third one, Deneb, is right here. It's not labeled, but this then is the summer triangle. We use that to help us find constellations in the summer. Speaking of constellations, let's turn these on now. I'll just show the lines. Sure, we'll show the labels too. And we can go ahead and turn the equator on as well. So that equator is basically the Earth's equator projected outward. As you can see, the Earth is at a tilt, which is why the equator and the ecliptic do not coincide. If the Earth were not tilted, then they would be superposed on top of each other. But the Earth is tilted at about a 23-degree angle. It varies over the millennia, but it only varies by about 3 degrees. So we have all these constellations. Now, these are not necessarily the same patterns that the ancient astronomers picked out, but a lot of them are similar. Today, our sky is divided into 88 constellations, and it's more so regions of space rather than patterns. But with how astronomy started, we need to take the patterns into account and try to use our imagination, see what we can see in there. So it would be best to start with the circumpolar constellations. And I'm going to change the view now. Let's go to a stereographic view. This projection, also originally known as the planisphere projection, preserves angles at which curves cross each other but does not preserve area. So I'm going to zoom in now. And let's go around. Now this is more like what you would see if you're there, except you won't see the green meridian line or these lines connecting them. But you can see that the two pointer stars of Ursa Major are pointing towards Polaris. Polaris is this star right here. Let's turn on the labels a little bit more so we can get some more labels. Great. So Polaris is labeled there, you can see. Now, why is Polaris, isn't that the North Star? Why isn't that on the meridian, like straight up from north? Well, the reason is I've gone to the year 2001 BC, and the Earth has a wobble in its orbit. This was discovered by Hipparchus. We're going to learn about Hipparchus in week 2, Greek astronomer. But yeah, if we go back 4,000 years, Polaris really isn't the North Star anymore. And there are other stars. Let's take a look at one night, kind of looking at the, actually, let me turn on the equatorial grid. This shows us where true north is. It's right there. And over the course of a night, well, daytime, it's kind of, you can still see the outlines of the constellations. And you can see these stars are all going around the north celestial pole. Now, if I jump ahead to the year 2000, now Polaris is really close to that. That's why it's the North Star during our lifetimes. Over the course of a night, you can see Polaris is really close to that. It goes around a little bit, but it's close enough that you can use that to help you find your way north. And these two stars of the Big Dipper of Ursa Major, they still point to Polaris. So it's pretty easy to find the Big Dipper in the sky, this pattern. It's probably the first one to memorize. It's the Big Dipper. These 7 stars are part of Ursa Major. As you can see, these lines connecting other fainter stars. And that would be the complete constellation of Ursa Major. But on most nights that are clear, you can find the Big Dipper if you're in the northern hemisphere and find these 2 stars to point to Polaris. Awesome. Now let's talk about planets. So we can see Mars is over here by these labels for meteor showers, the Theta Ophiuchids. Ophiuchus is the one constellation that the ecliptic goes through, but it is not counted as part of the zodiac. Technically, there should be 13 zodiac constellations, which are the ones that the ecliptic goes through, but since we have 12 months of the year, people decided they had to leave one out. So Ophiuchus got left out. Anyway, Mars, let's fast forward one day at a time. We can see the motion of Mars, moon flying by. Motion of Mars compared to the fixed stars, you can see it's going to the right, getting closer to that meridian, closer to Antares. going to have to bring it back into view here. So it's not staying in the same spot compared to the fixed stars. Hey, and then it's starting to go left again. So planets are wandering around. The name planet comes from the Greek planetes, which means wanderer. That's where they got that name. Mars is the one whose motion is the fastest out of the outer planets. We could look at Jupiter, Saturn, Venus, or Mercury. In fact, let's look at Venus next. That'll be an inner planet. Jupiter and Saturn would do the same thing as Mars, but just on a slower and more subtle basis. But Venus, all right, so here's a good time. Venus is further away from the sun, so the sun has just set in the west, but Venus is still in the sky. And it's always going to be close to the sun, so it doesn't get too far away. But if we fast forward one day at a time, you can see there are times when it gets up a little bit higher. But then once it gets to its greatest elongation, then it'll start getting lower again. As it orbits the sun. Mercury, same thing, but Mercury stays even closer to the sun. So that's how Mercury and Venus appear. Mesopotamia, the land between the Tigris and the Euphrates, is where Western astronomy began. We will focus on the Sumerians and the Babylonians. It's important to take into account that at this time, astronomy and astrology were not yet separate. Today, astrology is not a science. Astrology is the idea that the positions of the planets in the sky has an influence on our life on Earth. The Sumerians, around 3000 BC, developed a form of writing called cuneiform and followed a 7-day week. Some of the Sumerians' names for stars later appeared in a Babylonian star catalog around 1200 BC. The Sumerians used a base 60 number system. They're also the ones who first divided a circle into 360 degrees and an hour into 60 minutes. The Old Babylonians are the first people that we have a record of that used math to try to predict when astronomical phenomena would occur. They recorded things like the amount of sunlight each day over the course of a year, and the risings and settings of the planet Venus and the other planets. The Babylonians got even more serious about recording astronomical phenomena in the mid-700s BC, and even figured out an 18-year cycle of lunar eclipses. They continued to keep records of ominous events for centuries and tried to develop math to be able to predict these astronomical phenomena without consulting past records. There are 3 types of calendars: lunar calendars, solar calendars, and lunisolar calendars. Lunisolar calendars try to combine both lunar and solar aspects of the calendar. Most of the calendars we're going to be looking at are lunisolar calendars. Now, it's important to understand that a year is never exactly 365 days long. Because the Earth's orbit is changing over time and its spin rate is slowing down, there can never really be a perfect calendar. So the Gregorian calendar's days are numbered. The Babylonian calendar was lunisolar. They had 12 lunar months and an intercalary month as needed. Each month began with the sighting of a new crescent moon at sunset, not a specified number of days. Babylonians around 700 BC assigned planet gods to the days of the week, and there were 7 known at the time: the Sun, the Moon, Mercury, Venus, Mars, Jupiter, and Saturn. During the Babylonian captivity in the 6th century BC, the Jewish people adopted the Babylonian names for months. Beginning in 499 BC, the Babylonians began to observe a metonic cycle based on the fact that 19 solar years are approximately equal to 235 lunar months. The Jewish calendar is also lunisolar. Common years have 12 months, 354 days. Leap years have 13 months, 384 days. So there would be a leap year approximately every 3 years, or 7 times in 19 years, depending on the moon. Deficient years, 1 day less, and complete years, 1 day more, were observed in order to prevent certain holidays from falling on certain days of the week. The year 3761 BC was determined the year 1 AM, or Anno Mundi, in the year of the world, by the Jewish philosopher Moses Maimonides. He considered that the biblical date of creation. The Roman calendar is the ancestor of our modern calendar. It was used in the Roman Republic until it was replaced by the Julian calendar. It originally followed the phases of the moon, and there were originally only 10 months, starting with March. That's why the month September corresponds to the Latin number for 7, septem, and October 8, November 9, December 10. It doesn't match up anymore because January and February were added by the successor of Romulus, Numa Pompilius. And before January and February were added, each year was only 304 days, with about 61 days unaccounted for in the winter. They just didn't belong to any month at all. Then Numa Pompilius added January and February, and we had 12 months in the Roman calendar. This calendar in the time of the Roman Republic was 355 days, so a leap month called Mercedonius or Intercalaris was added every 2 or 3 years. Inserting the leap month was initiated by the Pontifex Maximus, the high priest of the College of Pontiffs in ancient Rome. So the length of the year then became tied to politics. If he had someone he liked in office, then he'd put a leap month in there. If there was someone he didn't like in office, he would say, no leap months this year. The Julian calendar was introduced by Julius Caesar in 45 BC. Julius Caesar consulted an Alexandrian astronomer named Sosigenes to tie the calendar to the seasons. It consisted of 365 days divided into 12 months, with a leap day every 4 years. Even today, astronomers use what we call Julian dates. This is to help us when there are discrepancies between calendars. So the Julian date 0 starts at noon on January 1st, 4713 BC, and it counts 1 for every day. At the Council of Nicaea in 325, it was decided that Christians should celebrate Easter on the same day. But they didn't have internet back then, they didn't have email, so how were they going to do that? Well, they could use an astronomical phenomenon. In fact, they used 2 astronomical phenomena: the full moon and the vernal equinox. Easter, then, was to be celebrated on the Sunday after the full moon, after the vernal equinox. They determined the vernal equinox as to always be March 21st. We know that it could slide to March 19th, March 20th, March 21st, March 22nd, depending on whether it's a leap year and how it's been drifting. So Easter is the Sunday after the first full moon after March 21st. However, because the Julian calendar wasn't exact, because a year is not exactly 365.25 days, the seasons began to drift through the year. And it was determined at the Council of Trent in the 1500s that the calendar needed to be fixed. Pope Gregory XIII decided he was going to do that. And in 1582, he instituted a calendar reform. We call this the Gregorian calendar, and it's the one we use today. This calendar was designed by Luigi Lilio, who died in 1576, so he never got to see the calendar he designed put into use. The Gregorian calendar realigned the seasons with the calendar. It instituted a new leap year rule. So you may think that leap years are every 4 years, but there are exceptions to that and exceptions to those exceptions. The exception is that if the year ends in 00, it's not a leap year. But then there are exceptions to that exception. If the other digits of the year that ends in 00 are a multiple of 4, then it is a leap year. So the year 2000 ends in 00. So is it a leap year? Well, the other two digits are 20, 20. 20 is a multiple of 4. So it is a leap year. But the years 1700, 1800, and 1900 were not leap years. The year 2100 will not be a leap year. Because the Gregorian calendar was an initiative of the Pope, only the Catholic countries followed it when it was instituted. England didn't switch over to the Gregorian calendar until about 1750. Russia didn't switch over to the Gregorian calendar until 1917, after the Bolshevik Revolution. But then the Orthodox churches still didn't want to follow a calendar that was instituted by the Roman Catholic Church. So they got a Serbian astronomer, Milutin Milankovic, to devise a different calendar. And this is called the Revised Julian Calendar. Milutin Milankovic lived in the first half of the 20th century, and his calendar is actually 10 times more accurate than the Gregorian calendar. It doesn't diverge from the Gregorian calendar until the year 2800, but it has more complicated leap year rules. So basically, the general rule is that it's a leap year every 4 years, but years that end in 00 and when they're divided by 900 have a remainder that is neither 200 nor 600 are not leap years. You don't have to remember that. Only some Orthodox follow the Revised Julian calendar, though. Most of them prefer to stick with the Julian calendar. Lastly, I want to talk about the Persian calendar, or the solar Hijri calendar, not to be confused with the Hijri calendar, which is lunar. In the Persian calendar, time reckoning is based on the Earth's movements around the sun. There are no mathematical rules to determine leap years. The number of days between two vernal equinoxes determines if the last month Esfand has 29 or 30 days. Thus, this is the most accurate calendar. It has only 1 day error every 110,000 years, approximately. This calendar was introduced in Iran in 1925 and in Afghanistan in 1957. The first version of the solar Hijri calendar, the Jalali calendar, dates back to the 11th century by a group of astronomers, including the Persian scientist Omar Khayyam. The disadvantage of a calendar that is decided based on astronomical observations each year is that you can't really plan ahead. You don't know if a certain leap day, so to speak, is going to be introduced or not. So that could be one advantage of the Gregorian calendar we use today, where things are decided way ahead of time.